Hello everyone. So I will take you to a little journey to Mars this afternoon. I will present some comparison from attenuation properties between Mars, the Earth, and also the Moon. But before to start this, I want to talk a little bit about the planetary seismology history. And actually, we were able to deploy instruments or seismometers only on 3 telluric objects. So the first one is Venus, as you can see it here, with the Soviet Venera mission. So it was a series of missions to Venus. And with Venera 13 and 14, they actually, so it's 2 landers, and they had 2 seismometers, 1 on each lander. So they were able to land on the surface of the planet and also to have a record. So the records are a little bit short because the instrument worked for between 1 hour and 1 hour and a half due to the high temperature on the surface. So by studying these records, unfortunately, they were not able to record any seismic event, but there were a lot of work made on the noise part. And then we will go to the Moon. So with the Moon, started with the Apollo mission. It's also a series of missions to the Moon. The first seismometer was deployed with Apollo 11 that you can see just here. It lasted like almost 21 days. And actually, it was due to the temperature on the surface of the Moon. So they did better for the next mission. They put a better thermal shield on the seismometer with Apollo 12, 14, 15, and 16, as you can see here. So this is actually the first seismic network that was built on the Moon. And at this time, it's the only one. So the mission worked for several years, and we had a lot of data. These seismic events are very different from what we observe on Earth. I will show you after that some examples. So we were able to have a few groups like impact that we don't observe actually on Earth. They also have shallow quakes, deep moonquakes, thermal quakes. At this time, there is no clear explanation, for example, for the deep moonquakes and the shallow moonquakes origin. However, till today, actually, we still see some publication made with this amazing data. And then Mars. So they started with the Viking mission. So Viking mission was composed with 2 landers, Viking 1 and 2. On both landers, they had seismometers, and the seismometer was fixed on the landers. So for the Viking 1, the seismometer actually failed, so they couldn't operate it. For the second one, it operated for 550 sols. So when we are talking about sol, it means 1 Martian day, which is a little bit from what we have here on Earth. So unfortunately here also they were not able to record any seismic event, and the reason is that the seismometer was fixed on the lander. So for this mission they were like 1 meter from the surface to get seismic events. So I can let you imagine how frustrating that could be. So then came InSight mission. And this time we actually add, here you can see an arm to put the seismometer on the surface of the planet. So InSight mission is actually a complete geophysical mission. So we had we had a lot of instruments. You had instrument related to temperature, pressure measurement. Actually, Alex, I don't know if he's here. Alexander has a poster on this data if you are interested to see what kind of work that have been done on this kind of data. And we also had here the HP cube instrument to measure the heat flow. And we will focus, at least this presentation, will focus on the seismometer CEs that you can see here. So it's composed of, we can say, 2 seismometers. We had the VBB with 3 components and also the SP. And so the main objective was to constrain, of course, the surface of the planet to see if there is a seismic activity and eventually to classify it. And also to give maybe some constraint on the formation of the planet. So I'll go here. So here you have an example of the different type of events that were recorded during the mission. What I forget to say just that the mission actually stopped here in 2023, December 2023, due to energy problems, because we had a lot of dust that were covering the panel solar here. All the instruments were actually green, so everything is working. So as the vacation are coming, if you're planning to go to Mars, cleaning the panel solar will be really appreciated. And so this is the kind of event, and we classified them into 2 major groups. So you have the first family, which is high frequency event, and the low frequency event. So this event, as you can see here, occur at different frequencies band. For the low frequency event, you also have 2 groups. You have BBB and LF event. And I think the poster of Alexander also talk a lot of the classification. So if you have more questions, you can talk with him later. And so my work, at least for me, is focused on these 2 kinds of events, the high frequency and very high frequency. Usually we observe them between, I can say, 2.4 hertz, and it can go up to like 45 hertz. And you can see here, this is a little statistic, but I think it changed a little bit with the last year. But what we observe is that the main event that we observed here are from the high frequency family. And here what I'm going to present is a study that I made on this event by using the very high frequency event, and also some near impact. So if we go to here, with this mission, we were actually able to make the first comparison between 3 telluric objects. So we have the Earth, Mars, and the Moon. And you can see here an example of seismic records on the 3 telluric objects. Each event that I selected here had a similar epicentral distance to the station. And they are all impacts are shallow. So for the Earth, it's a crustal one. It's like 10 kilometer depth. For Mars, we still have some mysteries, so we don't know exactly, but we think it's shallow. I will show you later some insights on some results on this hypothesis. And this is the Moon. And you can observe clearly that the duration of the 3 events, it's quite different. So for the Earth, we are very lucky because we observe clearly the P and S arrival here, which helps for the localization, as you all know. And you can see also that the direction of the coda is quite short. You can see it here. On the Moon, we have something actually quite different, because you observe here we have a lot of multi-reverberation and diffusivity that you can see here. So the signal is very diffuse. Usually we can identify clearly the first arrival, but we have difficulties, and sometimes it's really impossible to identify the S arrival. And the duration also is very long, because it can go to more than 2 hours. On Mars, we have actually something between the 2. telluric object. So we observe the first arrival here, P. We also observe the S, that you can see it here, and the coda duration is a little bit shorter. So when we have a first look to this event, we may think that these differences that we observe here are directly related to the velocity model of the structure. But in fact, if we do an average of the velocity modeling of the crust for the three telluric objects, we find something very similar. So the estimation here are very similar. So the main difference that we are observing here is directly related to the attenuation property of the medium. So this is why understanding and constraining the attenuation in planetary field is very important. And so here I want to show you just an example of the very high frequency event. This is actually one of the first very high frequency events that we recorded on Mars. We were very excited to see it. And then it was very depressing to understand it. So, so here you have the east and north complement. And what we tried to do here is to study the polarization of these two components. We didn't use the vertical one here because we want also to avoid some side effects. And what you can observe here, for example, for the SNR, you can see clearly the event, the seismic event here, and you can see some injections here. And actually, what we are looking at here are wind injections. So you can see them before and after the event, and a little bit during also the event. But what is really interesting here is that we observe that the signal is actually depolarized. You can see it here for polarization. And it also follows a Gaussian distribution. So these two characteristics are actually indicating that we are in a multiple scattering regime. And I want also to show you an example of the near impact that we found very close to the station. You can see here is inside, and we found actually at now, I think, 4 near impacts, maybe. It's 6 now. Okay, it changed a little bit. I have to update that. But I will focus here only on these 4 near impacts. And so we were really lucky to observe them, and actually we identified them due to this weird signal that you can see here, which is chirp, resulting from the explosion actually of the meteorite in the atmosphere that you can see here. For example, for this example, I think this one is the 986C, and you can see here you have 3 blasts and also 3 chirps here, and this is actually the seismic signal. And so now I will go to the next slide. So here what I will try to present is really focusing on the attenuation properties. When we are talking in attenuation, usually we are talking about 2 main mechanisms, the scattering and the absorption. So if we talk about scattering, we are talking about the characteristic of heterogeneities and also the fractures in the medium. So you can see here, for example, this is a shortcut for Mars. And you can see that we see clearly that we have a lot of regolith, and we can use this parameter to give, for example, estimation of the thickness of the regolith. What we can also do is the absorption. So for the absorption, we observed clearly on the surface of Mars ancient remain of rivers, and there is a lot of model who actually suggest that Mars used to have a lot of water in the surface. And this model also suggests that the water actually evaporized, but some ancient remain, very small amounts, could be at this time in the crust. So by estimating the absorption, we can give, can say, an approximation of the medium. So if we actually have small amount of water or no on Mars. So to do this, we have we used actually two methods. The first one is kind of empirical. We work directly on the envelope, the energy envelope. So here you have an example of this event. It is a very high frequency event filtered at 7.5 hertz. What we can do is a direct measurement of the delay time that we defined as the time from the S here, direct S arrival to the maximum of the energy. And the second parameter is the coda quality factor, which is described the decay of the coda. We applied this measurement on all the very high frequency and also the impact. And so if we start first with the delay, you can see here the result with a comparison between Mars, Earth crystal region, and also the volcanic region. So you have the delay as a function of the frequency. What we observe here on Earth is that we had a frequency dependency of this quantity. It usually increases with the frequency. On the Moon, we observed actually something quite different. We observed the opposite. This quantity decreases with the frequency. At this time, we don't know why. It has been a lot of research, but they think that it's directly related actually to the properties of the medium from the crucial part. And on Mars, we saw something also completely different. It's that this quantity is actually stable, so it's independent of the frequency. And we don't know exactly why, but we think it's directly related to the scattering and the absorption. For the coda quality factor, so here you have a similar example. You have the near impact here on Mars and also the very high frequency. And here, so what we saw that we used this empiric formula here to quantify, I can say, QC for just a comparison. What we observed is that for the very high frequency here, we need that the component is very stable. It is really equal to 1. When we have a high value of Q0. On Earth, we observe high value of Q0 only in the Cretan region, as you can see here. However, the exponent is like 0.5. So on the Moon, it's kind of similar to the Cretan region also. So with this comparison, we had a first overview of the attenuation properties, and we may think that what we are going to obtain with our inversion is estimation that will be between what we observe on Earth and what we observe on the Moon. So now we want to separate the two mechanisms, because what I showed you before, the two empirical variables actually are both sensitive to the scattering and the absorption. So if we want to separate both, we use the radiative transfer theory that was perfectly introduced to you this morning. So I will go a little bit fast on this slide. But just to remember that this is the very pretty equation that we have when we work on the radiative transfer theory. What is important to keep in mind is that you have a term here that is directly related to the loss and by scattering and absorption. You have here a term that is directly related to the gain by scattering, and also the term of the source. So what we do in our inversion is that we actually inverse times. And then we use this equation here to talk about quality factor of scattering, absorption, and also I will show you some result with the diffusivity. So the diffusivity here is important because it regroups both the scattering for the P and S wave, but it's also independent on the frequency. So if we want to do a comparison between the different other studies who were made on Earth and the Moon, it is easier to use the diffusivity because sometimes we all not work in the same frequency bands. So for the inversion, what we do is that we use the energy envelopes, that, as you can see here, as inputs. We fix the velocity model and, of course, an estimation of the event location. And we started our inversion by using this simple velocity model. You can see here the crust is about 40 kilometers. And what we did is that we inverse actually the scattering and absorption only in the first layer. So here, for example, it's 20 kilometers. And so this is the result actually that we obtained. You can see here the very high frequency event, and here the near impact. So this is the real data, and this is the synthetics. And what we observed is that with a diffusive layer of about 20 kilometers, we can retrieve pretty well the shape of the envelopes for the near impact, as you can see it here. And the scattering and absorption coefficient, you can it indicates that we have a lot of scattering and very very low absorption. So we don't have that much water in the medium. However, if we take a look to the very high frequency event, which are more distant events, in this case, you can see that our simulation doesn't work that much. So the main issue for us was here the flattening of the P coda that we observed clearly on the very high frequency event, and we couldn't retrieve here with our simulation. So to answer this question, we worked a lot, on the different parameters. We tried to check a lot of things, but we were able to have a final hypothesis with this event, which is the 1222I. It is the most energetic seismic event that we get on Mars. It's most 4.7 magnitude. So with this event, we were very lucky because we observed actually the surface waves. And there have been several studies using this event with several methods, including polarization of PS wave and also surface waves. And in the end, they proposed 3 locations of this event. The first one is here in the northern plain. And the third one is here in the northern highlands. So what we try to do is to inverse the envelope of this event, as you can see it here in black. So this envelope is filtered at 7.5 hertz by using different models. So what we tried to first with what we found with the near impact model. So it's here the first model with 20 kilometer diffusive layer. And it's the model in blue. You can see that the shape is quite different, envelope shape. What we try to do after is to increase manually the scattering and absorption in the lower layers, so here in the crust. And we observed that we started to see an amelioration. So it's the green envelope here. So then we actually suggested that the diffusive layer could be actually thicker, and we used 60 kilometer depth for this diffusive layer. So due to a problem of the inversion, so we supposed that all the crust here is actually heterogeneous for this first test. And actually, when we increased the depth here of the diffusive layer, we started to see an amelioration. You can see that we retrieve here pretty well the flattening of the P coda. So here are the results for the 3 models of the inversion in the first layer. So you have the scattering and absorption. And what we saw that with our best fit here, the results of the inversion correspond to what we observed with the near impact. So this diffusive layer has actually similar properties. So what we did after is that we applied this similar model to the very high frequency event that you can see here, other events. And we actually retrieved pretty well the shape of all the events. So you have the very high frequency event here and the near impact just here, with similar attenuation properties. So this was the main result of the research, because in the end what we concluded is that on Mars the scattering source is actually directly related to the presence of heterogeneities in the crust. It's not like on the Moon. The Moon is really the depth, the extended depth of the fracture in the medium, who can reach to between 60 and 80 kilometers. And with this result, so we suggest that, as we already have some studies on the thickness of the crust on the Moon, we suggested that the event, the 1222, could be really on the southern highland, or at least very near to the dichotomy. That's for the location. And so we worked also on the source. What we tried to do here, we used this event, and this time we changed the depth of the source. At first was supposed that it's an impact, and then we suppose that the source is actually deeper, so 10 kilometers in the diffusive layer and 25 kilometers below the diffusive layer. So the results are here. You can see that if the source is an impact or in the diffusive layer, we don't observe at all any difference between the two envelopes in our simulation. However, if it's below the diffusive layer, you can see that we have a very some arrival here that you can see one here, 3 here, which is quite different from what we observe in our data. So from this study, we concluded that the source of the very high frequency event could be only impacts or in the crust, so very shallow events, at least in the diffusive layer. And so to conclude, this is just a reminder of all what we saw with the study. So the main, we still have main questions. So for example, the fact that the delay time is very independent to the frequencies, still something I think we have to work on this here. What we also observed is that for the near impact, so we suggest that the thickness here near to the landing site of inside of the diffusive layer is between 20 and 40. When we go at higher distance, it have to be extended actually to at least 60 kilometers. And with this result, we were able also to make a comparison. Sorry. Maybe before to go here. That's one. We tried to understand the context of this result by making a comparison between the Earth, Moon, and Mars. And here, so you have the diffusivity as function of the attenuation properties. And so once again, I use the diffusivity because it is independent of the frequency. In a lot of articles, we don't work in the same frequency ranges. And we found this very interesting article of Takeshi, who actually used the comparison between 2 seismometers. So you have one seismometer here in the ocean, and the second one here near to the mountains. And he made a comparison between the envelopes at low frequency and high frequency. At low frequency, the waveform actually is kind of similar for both seismometers. But at higher frequency, you can see clearly that it is quite different here. For the continental part, it's in green, and the oceanic part, it's in red. And this is actually quite similar to what we observe on Mars. So by doing some diggings, also we found this article about the diffusivity in the oceanic atmosphere of Hinman of 2022, where they suggest actually that the diffusivity is between 15 and 60 kilometers square per second. So the blue that you can observe here, which is quite I have said the estimation is very near to what we see on Mars. So Mars here is really between, at least from diffusivity and also absorption, between the moon and the Earth oceanic lithosphere. So with this comparison, we suggest that maybe the strong scattering that we observe, which is on Mars, which is directly related to the heterogeneities of the crust, could be related to the basaltic origin of the crust. So actually, I would love to talk about that with some experts, because we didn't find that much diffusivity, absorption, or scattering research for the oceanic lithosphere, and precisely at high frequency. Usually our people work really at low frequency. It's a little bit frustrating. So if you have any comments or suggestions, I would love to talk about that after. And here is just the last slide of what we are working on now. This one is the nearest impact that we found near to the station. Here, the 1034.8. And with our inversion, you can see here, we found that we retrieve the shape of the envelope using two models. So one with 20 kilometer diffusive layer, and the second one in 15 kilometer diffusive layer. But the 15 looks better. So the aim objective here is to use this event to eventually have an estimation of the regolith, because what we found now is an estimation of the diffusive layer, which is directly related to the crystal heterogeneities of the medium. But what we really want to do is to estimate the thickness of the regolith, at least near here, the landing of the station. So we're planning to do this by ameliorating our code using eventually a Monte Carlo code and a multiple inversion of the multiple layers, because we had some issues with the actual code. We cannot do multiple inversion of the different layers. So that's the main point. Thank you for your attention.